Welcome to a new test and teardown video. This time it's a Panametrics Ultrasonic Gage Model 5222. The idea with this instrument is you have a transducer, an ultrasonic transducer, and you put this to a material and you put in the velocity factor of that material, and then it sends out a very, very fast pulse. I think it is about 20 megahertz, this pulse. And then it measures the travel time, the reflection from the other side of this material, and then recalculate with the velocity factor the thickness of the material. So, can you figure out what this can be used for as well? If you know the thickness of an unknown material, you can poke around with the velocity until you have a readout of the exact thickness of your material, and then you get the velocity factor, and then you can look up in a table and figure out what is the material you got. So I think this is the most interesting thing I wanted to try and use this for, if I can get this up and running. The rear side of the unit, we got 4 BNC connectors. The idea is you can connect these to an oscilloscope, and then you can see the pulses and the reflections and everything like that as well. This helps you to see the signal quality, all your levels and all your reflections. And this way you can see, is the sensor correctly mounted to your material and all those kinds of things. And there's also a charge power connector here, and it's very, very heavy, so I expect there will be a battery inside. It looks like there's only one screw here on the back, so let's have a look. It's actually surprisingly beautifully designed. And I'd like to show you a super sexy detail about the case. So there's only one screw in the case, and a very long kind of special screw. Look at that, even the thread and everything here is really, really special. But that is a really nice detail. In all 4 corners, we got those little holes and those pins, and they align perfectly fine and hold the case completely good and stable with just one screw. That is so nice. So I'm not super surprised to find a big heavy lead acid battery. Here is the type number, 6 volts, 3.2 amp hours, and they've got a little connector here, so it's quite easy to remove. I mean, they rarely leak, so I kind of like when they are still in the instrument, because now it's easy for somebody in the future to figure out what kind of battery to put in, how many volts, how many amps, how many this and that. So this information will get more or less lost if I just remove the battery. If you have a battery type that is most likely to leak, of course you want to remove the batteries, but please take a permanent marker and then write the type number and the voltage, the currents, the whatever that is relevant for the future. Just put it in there, because you're gonna forget about this in the future, or somebody else after you want this information. So that is a good advice. And yeah, what else can we see here? I didn't expect it to be that old. Look at the date code 75. That one is what? I can't see that here. Gotta get some better photos of the different. Okay, see here, 79 on that one. So it is, yeah, quite old. I think I know already how this one works. So we got probably this is a reference of an oscillator, and that is of course used because it sends out pulses, and the timing here is super, super important. And there's probably a little frequency counter, timing counter out here. And there's also a little crystal. I think I saw yes, there's a little crystal down there. So that is a little bit weird. Why would you have that and not using the main reference? And then the calibration for velocity, that's just done with some resistors like that. So this affects the timing constants of this unit. So yeah, I'm a little bit confused about how that is done. So the velocity goes down here, and this is the white cable that shielded and go in here. So it's those signals. Okay, so all this velocity stuff goes to this one. So this is the timing as well. See, we got a lot of high precision resistors and all that kind of goodies. You can take out the boards quite easily. A power supply, also a little charger. See, we've got all the different voltages written here, so it should be fairly easy to figure out what is going on. Aha, it says T1. So there's a transformer, a little switch mode converter. And we got some transistors here and some stuff for that. Okay, so this is a little switch mode converter. And this is, of course, now I got it. Yeah. We got a single 6 volts, and then it generates all the different voltages and stuff from this little switch mode converter. That is quite nice. We got some thallium capacitors. Ooh, I don't like them so much. And a little fuse in a socket. Beautiful design. So this battery measures 0 volts, and I just try and disconnect this the battery and input 6 volts from my power supply, and it is not using any kind of current, so it's completely dried out and yeah, open circuit. So we can just put this back again so we don't have any loose connections, and it's not going to cause any damage to the charge circuits or anything like that. So that was a little bit what I was afraid of. I'm going to power this up now, and how about that? And that's all it does. When I power it on, we just see this but I think there's a possibility that this is normal because there is no sensor mounted. So it's just checking out something, and then there is no reflection, and then of course it's not showing anything at all. See, that's probably what's going to happen. So I need to go and repair this sensor. And before I got the idea I needed to repair the sensor, of course I went through all the voltages. We got some different test points. So we got positive and negative 5. We got 12 volts and all that. And there's another funny thing. Up here we got plus 100. And I think this is for the sensor or the transducer. So they ping out a real loud pulse. And so there should be some sort of a power driver somewhere. It's probably that one, right? And then I don't really see any power transistors, probably because I'm not looking carefully enough. Probably that tiny little one there. Really? But the sensors, they're really, really small. And this one is broken. We've got this LEMO connector. I like LEMO connectors. They're very, very expensive, but they're also very, very good. So here is what appears to be a connector. See? And here is the sensor. So the other part of this connector here was supposed to, go out of the back side of the sensor, and the sensor itself looks quite intact. So it's really, really tiny. And it even says some different names and numbers. So this is it 116 M and then 116. So my idea is I'll try and see if I can scrape the way down to the connection down there. If I can't do this, then there is no way I'll be able to save this or repair this in any way. I don't know if I have a connector that will fit for this. Well, so that is my little challenge. I think I was able to dig out a little piece of this. Let's see, there's a little red wire in there. So I think this is how it's assembled. So all I have to do now is solder a little wire to that one. So I am a little bit, I don't know, I have different feelings about what to do, because this is the cable and there's a LEMO in the other end. This is a rather expensive cable because of the LEMO, I guess. And this connector here is called a microdot. And I don't have either male or female mating connectors for a microdot system, so that would of course have been the best way to repair this. But while I think about what to do about that, I will try and see if I can measure if I actually got access to the transducer. That is not looking too good. See? I soldered to that one, and the result is only 0.7 picofarad at 100 kilohertz. I mean, this is the same as not connected somewhere. So it's unfortunately blown up, and this is probably why. I mean, somebody cracked it or something. They tried to open it and see if they could repair it. Yeah, the sensor is definitely not working. Darn it. So far I'm getting a little bit used to. I'm not going to be able to play with this in its intended condition because this damn sensor, I believe, is broken. But anyway, I might as well just enjoy the rest of the funny details here in the design. So this will be the readout, and that ICM 7208 is a frequency counter, readout, multiplexer, and everything is included inside this chip. I believe I have already shown this chip before. It's data sheets and specifications and all this. It is in many of the cheaper frequency counters and all that. And we can also see here the connector. It's a quite nice connector, by the way. You see, it's not so deep. Normally those edge connectors, they are a lot bigger. And this is because the mating connector on the other circuit board, look at the different. This is a very, very nice and special type. And they are really, really cool. So they require your PCB not to be that long and deep. Okay, by the way, the date codes, they puzzle me a little bit. So this one is for 78. And why is it always out of focus, this annoying thing? 79. So now we are in, let's read the date codes distance. see, 79. And it goes on and on. A lot of them. Oops, and yeah, another one, 79. And here is the side circuit board right here. This is directly connected to our sensor. That will be those 2 pins right there. Oops, where are we? Here we are. So that is our piezoelectric transducer and sensor thingy. And I believe this is, of course, ground connecting to chassis. So the other one is that one. Goes to that transistor and stuff right there. So this is the driver transistor that gives pulses up to 100 volts. This one is from 76. And then we got some amplifiers from 1975. MC1590G. So that will be wide frequency band, high gain amplifiers with ADC. So they are somehow adjusting the gain over time, and this is typical because the echoes gets weaker and weaker the longer it takes, because the signal travels through more material. And to be able to pick up the echo and trigger on it, so that will be our trigger. And so they're using a system that changes the gain of the amplifiers here over time. So definitely how you do this, and this is a quite normal method, by the way. Oops, this one was changed. But it's also... What is it? I struggle with the focus. 83. So it went for service. And it was not the first stage that broke. Oh, look at that. We got some diodes here protecting the input. So that means while you are driving the transducer, the signal that goes into the amplifier chain is just clipped to a diode level, and then all the millivolts that comes back gets amplified a lot of time, 50 times, 50 dB and 50 dB. I mean, so that is a lot of dBs. Just wanted to show the name pulsar receiver, and the is of course just display logic. I haven't given up completely. Well, I know my sensor is not working, so why not just try and measure exactly what it is it's doing. It should send out a 20 megahertz pulse and then wait for the echo. And since there is no echo, the screen just turns off. I think this is what we see here, right? But I can of course measure this pulse on my scope. See, it's 27 megahertz, and the repeat is 180 hertz, more or less. So this is how often it sweeps, or it measures this. And since there is of course no reflections, nothing really happens. So I can't get a lot further with this unit. I could try and see, can I make an echo and somehow trick this into displaying at least something, just to see if this unit is potentially okay. And then maybe I will be able to find another transducer in a better future. I don't know. I think I figured this out. So here's what I do. I connected a little reel of ultra thin coaxial cable to my test point. The voltage divider here is not really important anymore. I was just a little bit afraid of the voltage. It is sending out about 100 volt pulse unloaded. But of course at the moment I have loaded the signal with this coax cable's impedance and all that kind of stuff. So anyway, it's not sending out a 20 megahertz pulse. It is sending out a rise time. So that's what it's sending out. And the transducer is resonant at 20 megahertz for this model, or you can have other models that is resonant at other frequencies. So it's all about the transducer. So it's a piezoelectric transducer, and it is resonant at whatever frequency for the type and brand and size and all that kind of stuff. Okay, so that is how the emitted signal works. And then there is this pulse. So this is the strong pulse. This is the exciter pulse. And since it's just a very, very powerful rise time, then you can imagine if you have a transducer connected with a resonance kind of system in it, it will go like bing, 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 and then it will dampen. And then you will get a reflection of whatever type or whatever. It's also going to look a little bit like a resonant kind of thing. And then the timing, here is the timing for this pulse and the return of a coax cable. So there is of course this is the propagation factor of this particular coax type. We measure the time it takes and of course over the length, and then you can actually look up all the properties of this cable and see that this is correct and all that. So what we got here is 118 nanoseconds, and this unit of course respond correctly to that pulse, and it convert this into thickness at exactly this velocity factor. So if I change the velocity factor, I should also change the thickness it thinks that we got. I'll try to put the camera right here. So let's try and play a little bit with this. Let's try and turn it on and off and see if that helps. Okay, so there's a lot of stuff here that just don't work. So all this velocity thing just don't do a lot. I don't know what to say. I think this unit just don't work, or at least it's not working exactly like I imagine, or this type of pulse that I have is not compatible somehow, but it's, yeah, well. Anyway, I cannot say a lot more about this unit. So I will end this video right here and right now, and I will say thank you very much for watching. I hope you had a little bit of fun, and feel free to comment if you know a lot about those type of sensors, and yeah, if you can contribute, please do. Thank you. Bye bye.